The t-distributions are a family of distributions with a similar shape to what we're used to considering a normal distribution. In this picture, we have a normal distribution as the one that comes up highest, and it also comes down the lowest in the tails. So this is a normal distribution, and we can see some t-distributions around it. To understand the t-distribution, we need to back up just a little bit to the central limit theorem again and the standard error formula that we use. So, looking at the central limit theorem, we see that the distribution of sample means for n sufficiently large is a normal distribution with mean mu and with standard deviation sigma over square root of n. If we go back to this idea of a z-score, think about an object in this distribution is a sample mean. So we're working with a sample mean x bar. So an object in this distribution is a value of x bar, not a value of x. I would subtract off the mean and divide by the standard deviation to get a z-score. Remember that the z-score is a measure of how many standard deviations an observation is away from the mean and in what direction, to the right or to the left. Well, once we start using this s in place of sigma, then that expression becomes this x bar minus mu over s over the square root of n, where s is calculated by this formula, and therefore this expression has a whole bunch of, it has a sum of a whole bunch of squares of the distance from each observation to the mean. The whole point of the t-distribution is that this object no longer follows a normal distribution. It follows what we would call a t-distribution, and what t-distribution it follows really depends on this formula here. It depends on the number of independent terms that went into that standard error calculation. We don't need to have a really solid understanding of this, of all the math behind it, to use a t-distribution, but it can be helpful to have some idea why we're suddenly switching from normal to t. It really has to do with the fact that we are now calculating our standard error using this formula s over square root of n, and that the formula for s is a sum of squares. So we refer to the t-distributions as a family of distributions. We have a different distribution for each number of degrees of freedom. The degrees of freedom are the number of independent terms in the standard error calculation. Now, the reason that isn't n terms, the reason we have n minus 1 instead of n, is because if we think about it this way, each of these terms is of the form some observation x minus the mean x bar. Well, if x bar is known, then we could back calculate the very last term if we wanted to. So it ends up being really n minus 1 independent terms, even if it is n terms total. What we really need to know is that if we're doing inference for one mean, we always have n minus 1 degrees of freedom. So it's always n minus 1 for inference about one mean. Now back to these curves, the one that I highlighted in pink as the normal distribution, it's probably hard to read what this says right here. This says n equals infinity. So the idea here is that as n increases, the t-distribution gets closer to the normal distribution. And that does make sense because our estimate of the standard error should also get closer to the true standard error of that sample mean, or rather our estimate of the standard deviation from samples should get closer to the true population standard deviation. And so what we see here is that for a small value of n, like 2, this one says n equals 2, we have a curve that's very far from normal. It's got less concentrated at the center and more mass in the tails. We can also call that thick tails. As n gets larger, like we see here for n equals 10, we do get a bit closer to a normal distribution. There's a little bit more concentrated at the center, and the tails get a little bit smaller. We get less mass in the tails as n increases. So the behavior of the distributions is very similar. The way we recognize an appropriate shape is about the same, but we need to know to use a t-distribution with the correct degrees of freedom rather than using a normal distribution when we're doing inference about one mean, provided that our standard error estimate did come from this formula. Now our rule of thumb for sample sizes, this is really based on the exploration we did for the central limit theorem. Our rule of thumb for sample sizes and using a t-distribution is that if n is less than 30, we really want to know some information about the shape of the sample. Does it look approximately symmetric? Are there any extreme outliers? Is there heavy skew? And we want to make a judgment call about whether we think that the sampling distribution would be close enough to bell-shaped to use a t-distribution. If n is greater than 30, then we generally assume that it's okay. There are certainly exceptions to this. If there are extreme outliers, then we might need an n that's substantially bigger than 30. So we may still be concerned about extreme outliers even if we have a sample size bigger than 30. But if we don't know the shape of the sample and we're just doing a very rudimentary checking of conditions, 30 is about where we make that cutoff point where we'd say it's probably okay to not know the exact shape of the sample. When we did our exploration, we saw that even our heavily skewed distribution was already starting to look a lot more bell-shaped at 20, and then it looked really good at 50. So you can already resolve quite a bit of skew by the time you get up to about 20 or 30, which is the idea behind this rule of thumb.